This video is about infinite limits by deduction. Now, in the context here, we are talking about calculus class where limits are defined. We've already discussed some notation for them, some graphical implications of limits, when they might not exist. So this is not the first video in the series, but it will help build on our skills in working with limits. Let's discuss some essential deductive properties that will be helpful in using this method. First of all, a value approaching or equal to a constant. Okay, remember the word approaching? That's a key word in limits. So if a value is approaching or equal to a constant is just a number on the number line, like a real number, divided by or over a value approaching 0, again, the key word there is approaching, is equal to plus or minus infinity, and the plus or minus depends on the signs of the numerator and the denominator, as we'll see. Secondly, though we've already discussed that infinity is not a real number, it's a symbol that describes unbounded increasing or decreasing, and it still works conveniently like a real number in these properties, so we'll note them. First of all, negative infinity is really positive infinity, just like negative 2 would be positive 2. So obviously infinity is not a number, but it works in the same way. Thirdly, infinity plus infinity is infinity. Fourthly, negative infinity minus infinity would be negative infinity. Okay, so some of those are pretty intuitive, but we can't take them for granted. We have to state them as we need to use them here. Now, there's an extra note we want to add, which is this. Notice infinity minus infinity did not show up as a property. That's because this is what's called an indeterminate form, and we haven't quite gotten to all those and what that means, so more on that later. Let's consider some examples here, and we want to determine the following infinite limits by deduction. Now, you won't always see this specified in instructions or in a textbook. Not every author uses this word deduction, and so it may not say find by deduction, but it may say find the infinite limits. And so instead of looking at a picture of a graph, we want to be able to understand how in a detailed analysis these limits occur and why they occur, and that's what this process does. So we're going to call it deduction because it's deductive in nature, but that's not the official name for it. The way I like to organize this process is by using a number line. So we're going to draw a nice large number line here, and this limit, the first example, says we want to find the limit as x approaches 5 from the left of our function, which is x plus 1 over x minus 5. Since x is approaching 5 from the left, we're going to go ahead and put 5 on our number line. That's the value that x is approaching. We care a lot about it. So notice the numerator being x plus 1. As x values are walking their way down this number line, I'm going to use pink for the numerator to distinguish the different pieces of this function here. Those x values would be simply increased by 1 in the numerator. It's x plus 1. So eventually, when x is 3, the numerator will be 3 plus 1, or 4. When we eventually walk our way down to when x is 4, the numerator is then 4 plus 1, or 5. Okay, and so you can kind of see what's happening here. The numerator is increasing as these x values increase when we're getting close to 5, walking up on it from the left side. What's very important about these values is that they are positive. Now remember, eventually, if you start far enough to the left, could you get a negative value in the numerator? Well, sure. If you go far enough to the left, these x values will be very negative, and when you add 1 to them, they would still be negative. So you would have a negative numerator value in those cases. But remember, we're approaching 5 from the left, so all we care about is kind of what's happening near the end of this journey here as we get close to 5. And when we do, we can tell these are going to be positive values in the numerator. We'll then take a look at the denominator. That was x minus 5. And in the same way, let's consider, I'll write this now below our number line, but we could start, again, as far as we want to the left, but eventually we're going to sneak up on 5 on the left side of it, which means we're going to get to these places where x is 3, x is 4, x is 5, And when we do, notice what's happening here. If I were to plug in 3 for x, when x is 3, the denominator would be 3 minus 5, or that would be, in other words, negative 2. Okay, I'll keep walking up closer to 5 on the left here. Eventually, x values would be 4. When I plug in 4, I'll have 4 minus 5, which would be a negative 1. Okay, and then eventually I would even hit values between 4 and 5, like what about 4.5 or 4.9, right? You can do this little exercise with any value that's walking up to the left of approaching 5, and you're going to get interesting results because, think about it, anything that's left of 5 is less than 5, and if I plug something that's less than 5 into this denominator expression, which is x minus 5, if I have anything less than 5 plugged in for x, but then I take away 5 from it, it's going to end up negative, and sure enough, that's what we're seeing in these little examples we've computed down here, the negative 2 and negative 1. So what we can say with confidence is that as long as we're approaching 5 from the left, remember, we don't actually get to 5 because then our function is undefined. We get close to it though, we're approaching it from the left, and as we do, these denominator values are negative. So go back to our little deductive properties above, and you can find that when you have a positive over a negative, which is what we have here, right? The numerator is positive, the denominator is negative. That is a case where you have opposite signs, which means you have negative infinity for our limit. So if you go back up to our notes, you'll recall that it's either plus or minus infinity for a case like this, and the plus or minus is determined by the signs of the numerator and denominator, and that's what we just discovered. Let's try a second example. This time we want to find the limit as x approaches 3 from the left of our function, which has a numerator of square root of x and a denominator of x minus 3 all to the 5th power. Well, just like we did in the previous example, we're going to start by writing out a number line that's going to hold our deductive analysis on it. And notice x is approaching 3 from the left in this example. So we're going to put the number 3 on our number line. And we care about what the pieces of this function are doing. And remember, when x equals 3, we actually have an undefined function because you can't plug in 3 for x down here, you'll get dividing by 0. But remember, the approaching language in limits, where the arrow is used, where you're approaching, means you don't actually have to get there. You're just approaching it. And that can seem weird, but it actually works out here. Let's consider first what the numerator is doing. Remember, we're approaching 3 from the left, which means you could start as far left as you'd like, but the end game is right in our picture here. We're getting close to 3 from the left, which means eventually, no matter how far to the left you start, if you're approaching 3 from the left, you're going to eventually cross 1 and then 2. Of course, all things surrounding those as well. But it's nice to have those in the picture, I think. When x would actually hit 1, crossing it from the left here, then we'd have square root of 1 for our numerator. When x becomes 2, as we keep walking our way toward 3 here, eventually our numerator is going to be square root of 2 there. Okay, so we're kind of increasing the numerator as we get closer to 3, but again, notice what's happening with those values. They are certainly positive numbers. As you get close to 3, in fact, you can't even put a negative value in that function. There's no domain there since it's a square root. But again, we care mainly about getting close to 3 from the left, and when we do that, numerator is definitely going to be positive. If we look at the denominator and do the same exercise, we're going to walk up again from the left side closer to 3. Notice what's happening though. When x is 1, if you plug in 1 for this denominator, you'll have 1 minus 3, which is negative 2 to the 5th power. But a 5th power, being an odd power, would mean any negative input will stay negative. So negative 2 to the 5th power is negative. Now when you get to when x is 2, again walking further down this line toward 3 from the left, then when you get to x being 2, you plug it in. 2 minus 3 would be negative 1 to the fifth, but for the same reason, that's still negative. And as you approach 3 from the left, you take a look at this expression x minus 3 that's in our parentheses in the denominator. Anything less than 3, which would be anything to the left of it here, when plugged in for x, if you take away 3, which is what this denominator expression does, it's going to be negative. And then when you put a fifth power to it, it's going to stay negative, which means our denominator will certainly be negative as we approach 3, no matter how close we get to it. Well, as our property says above, when you have opposite signs, the numerator being positive, denominator being negative, those determine that we have a negative infinity value for this limit, because a pair of opposite signs, one over the other, is always a negative result. That's true all the way back to arithmetic. There's nothing different here. Let's consider a third example. This time we have the limit as x approaches 0 from the right of the natural log of sine of x. So it's a composite function where the inner function is sine of x, the outer function is natural log of x. In this case, rather than a single number line to kind of hold stuff together like we used in the previous examples, I think it's actually better to analyze the inner and outer functions separately before we try to put it all together. Let's take a look first at the inner function, sine of x, and recall that sine of x as a basic graph intersects the origin, and then of course it's a periodic sinusoidal graph. It just keeps wiggling up and down, but we know that it does intersect the origin and is positive to the right of it, up in quadrant 1, most immediately to the right. So think about just this for a second. Of course, 0 is at the origin there. As x values are approaching 0, they're walking their way down this number line toward 0. What's happening to the sine values? Well, the sine values are all the outputs, or you could say like the y-coordinates of all the points on this sine graph. Aren't those coordinates, those y-coordinates, as you get close to 0 especially, aren't they positive but decreasing as they approach 0? In other words, these sine values are approaching 0 from a positive state, which means they're approaching 0 from the right. Okay, hold that thought for a second. There's going to be a lot coming together here. Let's also recall, I'll use a different color, some kind of turquoise color for this, that the natural log of x function, if I were to recall what a sketch of its graph looks like, it has a vertical asymptote right on the y-axis. It would have an x-intercept at 1, 0. Kind of pull back your pre-calc or college algebra to recall that the graph for natural log of x will then plummet down toward that vertical asymptote, which as it moves to the left toward the y-axis. Okay, so let's see if we can put both of these together. And notice we're not doing this on a singular number line. We're kind of just putting them both together in a graphical form. If you take the inner function, sine of x, we discussed already that that function is approaching 0 from a positive direction, which means you could say that the sine values are approaching 0 from the right as x approaches 0 from the right. Okay, the sine values would be like these y-coordinates of this graph walking down. The x values are approaching 0 from the right, but they're both plummeting down toward 0, which means I can go over to the outer function, the natural log function, and instead of writing the x, remember it was natural log of sine of x, so I can say natural log of 0 from the right, because that's what sine of x is doing. But notice what's happening in our natural log graph. As I go to 0 from the right, the natural log values are plummeting downward as the natural log graph does toward that vertical asymptote forever. So in summary, what are the natural log of the sine of x values doing? Well, they're plummeting downward forever, which means we could say this limit should be negative infinity. Let's consider a fourth example. This one is the limit as x approaches pi from the left of cotangent of x. Now, we're going to have to bring out some trigonometry to recall some things here. So let's also remind ourselves that cotangent of x is really cosine of x over sine of x. Okay, if trigonometry seems a little rusty, maybe brush off a couple of things you might need to hear. Now, if that's what cotangent is, instead of analyzing this on a number line, I think it's actually easier to analyze this on the unit circle. Now, depending on how and where and when you had trigonometry, you may have had different experiences with, how you learned it or how much you used the unit circle. I'm going to rely heavily on the unit circle because I think it's very useful here. I'm still going to look at this fraction where you have a numerator of cosine and a denominator of sine as individual parts because I think that's helpful to understand. Are we talking about something positive or negative here? And instead of putting what x is approaching, which is pi here, on a number line, we're putting it on the unit circle. Remember, pi is way on the left side in terms of radians. If you think of the unit circle like an arc, then 0 is on the right side, pi over 2 is at the top, pi is at the left side, just to kind of remind you, 3 pi over 2 is at the bottom. So really, hopefully you have some of this memorized, ideally all of it, but there are some key places surrounding this unit circle that we're going to depend on here. Now, as x is approaching pi from the left, this is where it gets a little interesting. What we're going to do is imagine a number line that's wrapped around this unit circle. So if I take a number line and throw pi on it, and then I'm approaching it from the left, really I'm approaching it from values that are less than pi, right? I mean, somewhere to the left of pi would be pi over 2, eventually pi over 4, and so on. I'm approaching it from the left, which means I'm walking through these values that are less than pi. Well, now think of the unit circle and where that occurs. That means I'm actually walking my way counterclockwise around this circle toward pi, which is the left side of it. That's the same thing as moving 2 pi from the right on a number line, but this number line is now just kind of like wrapped around the unit circle. So a lot of visualization going on here. But if I look at these pieces separately, cosine values in this quadrant 2 where I'm approaching pi will all be negative, because in quadrant 2 cosine values are negative, and that's true all the way up until you actually get to pi. Sine values in quadrant 2 are actually all positive, and that's true as you're approaching pi. Now when you actually hit pi or get to it, of course now the sine values are 0, but remember, the approaching language of limits is what allows us to say, well, we don't actually have to get there. We're just approaching it infinitesimally close. And so we're getting closer and closer to pi, which means these sine values, though they're getting smaller, they're approaching 0, they're still positive. Because of this analysis, we can say that the numerator, which was the cosine values, those will all be negative as we approach pi here. The sine values will all be positive, as we just stated, which means in summary, we have a negative over positive, which would be a negative infinity for this limit result. Now, this is a fairly tricky example, especially when you throw the unit circle in here, because one of the most common misunderstandings is when students say, wait a minute, I thought we were approaching pi from the left. And if you walk down this unit circle, you're kind of like approaching it from the right. What's going on? Well, I know, but that's why it's helpful to see both pictures, because we're actually approaching pi from the right in terms of a number line. On the unit circle, we are kind of walking down the left side of this circle, which appears like we're approaching it from the right, but we're not. In the number line sense, we actually are approaching it from the left in terms of the values of the radian measures on this unit circle. Let's try a fifth example. This one states we want the limit as x approaches 2 from the left of, it's a rational function where the numerator is x squared minus 2x and the denominator is x squared minus 4x plus 4. Now right away you can say, oh, we did rational functions before. That was our first couple examples. And we set up a number line, we put the value x was approaching on it, consider the direction. So if we're approaching 2 from the left, we're walking our way down toward 2 from the left. Problem is, This one is less simple. In other words, if you look at the numerator and denominator, they're much more complicated as far as, will the numerator be positive or negative? How about the denominator? You can still figure it out by just plugging in numbers that are approaching 2 from the left. But in a case like this, there's another good strategy, which is maybe we could actually simplify this fraction. So let's rewrite this limit as the limit as x approaches 2 from the left of, and then let's try factoring this rational expression. The numerator is such that we could factor out an x, that would be x times x minus 2. The denominator is such that we could use an x minus 2 squared, a perfect square. But then notice what would happen here. The x minus 2 factor in the numerator would cancel with one of them in the denominator, which would mean really our function is the limit as x approaches 2 from the left of x over x minus 2. Now all of a sudden it's much simpler looking, and we can still do the number line analysis. It's just way easier with a simpler function. So let's put the value that x is approaching down here, which is 2. We're approaching it from the left. Let's take some pink to the numerator here. As the x values approach 2 from the left, remember you can start as far as you want to the left, but as you get close to 2, those values will eventually be 1, 1.5, 1.9. Okay, and the point is they're positive values as you get close to 2 from the left. If you look at the denominator, those are the x minus 2 values. But again, when you get close, like when you get eventually to where x is 1, then plugging in 1 would give you a negative 1 here. When x is 1.5, you'd have negative 0.5 for this denominator as it gets closer and closer to 2 with x values, which means those will stay negative. Remember, we don't get to 2, we approach it. That's the key word here, which means this function remains defined as long as we don't actually hit 2. Okay, but in summary, with a positive over negative, we could say that this limit eventually turns out to be negative infinity. Let's consider a sixth example. This time we have the limit as x approaches 0 from the right of the following function. It's 1 over x minus natural log of x. Let's treat these two terms in our function separately, where the 1 over x we look at separately. I'll use pink for that one, and then the natural log of x, we'll use this turquoise color for that one. First of all, recall just some basic graphs. I think this will help. 1 over x is a function whose graph has a couple branches, one in quadrant 1, one in quadrant 3. It has a vertical asymptote right on the y-axis. And so notice, as x approaches 0 from the right, which is what this limit is doing, we're walking our way down the function, or down toward 0 from the right. Notice what's happening with these function values. It's only this branch here in quadrant 1, and those values keep increasing as this function is now going to chase the asymptote upward forever. So what we can say is that this piece approaches infinity as x approaches 0 from the right. That's what this upward arrow would indicate in that graph. If we look at our second function, this is the natural log of x. We've already recalled there's a vertical asymptote on the y-axis here as well. We saw this one in a previous example. And the function plummets down toward it as x approaches 0 from the right. Which means, since that's what's happening in this problem, this function is approaching negative infinity. Now, if you put these two values together in an algebraic form, notice we really have the first one, which is infinity. There was a minus sign between those two terms, so I'll put it there after the infinity. So infinity minus, and then the second term value is negative infinity, as we discussed from the natural log graph. So really we have infinity minus negative infinity. But if you go back and look up at our properties for deduction, these infinities, though not real numbers, work like real numbers. We can call this infinity plus infinity, which is really just positive infinity.